Hello, this is our lab deliverables. So I will upload these documents. Lab 9, what is the PID controller? It makes the system fast as mentioned here, but along with that it increases an overshoot if this is a second order system, and makes the system more like spring type effect. So the PI controller, it is used where you want to remove the steady state error, and PD controller is used where you want to make the system more stable, and PID is a combination of all these three. Now the deliverables I'll show you in a bit. So you will read the theory over here, and I'm going to show you what to start. This is the the one which you want to understand, that the KP is a PID controller is written by KP will reduce the steady state error, but it will never eliminate, it will reduce. After a certain limit, increasing KP will cause overshoot. Increasing KP reduces the rise time. These are the benefits of using the PID controller. Then we have this lab is more about the PID controller using the Simulink models. So this is the PI controller. Integral control eliminates the steady state error, and after a certain limit, increasing Ki will only increase the overshoot. Increasing Ki means integral gain reduces the rise time a little. Let me go over to page sorry, this is I have to go over to this as well. KD, the gain, the D controller, which is the derivative controller, increases the increasing this gain decreases the overshoot and reduces the settling time. So you don't need to like work on the loop tuning. This you can leave this page, you can read it for your knowledge, but this is not a lab 9. The lab 9 starts from page this 14. As we have done Simulink modeling before, you will draw these models into Simulink. So let me show you the Simulink models here. So this is a Simulink model similar to this one, and you will use this first order transfer function, and this is given over here. This is 1 over s plus 1, but for this lab you will use gs equals to 1 over 0.1s plus 1, and for the second order transfer function, this is, let me change this one to this transfer function, you will use this transfer function to complete this these 4 plots. The reason what I mean to show you that what is the effect of increasing the gain on the controller. So let me show you one thing very quickly. So if you run this and you go over here, see this scope, you can find out the rise time from here. Go to the third icon here, it will tell you the rise time here, which is 353 millisecond, and you know the rise time is equal to 2 times 2 the time constant, and you can also find out the overshoots, which is about 0.5%. Actually I don't see any overshoot here, so it's about 0. So in order, then you will just copy to clipboard and put it in your notebook here. So if I show you, so you can bring it over here, and that's how you will complete this figure. So then you will be I was trying to explain you here. Okay, you will, let's do this for the other transfer function, the one with this one. I want to use another transfer function just show you how it looks like. Okay, by the way, first we have to do the other thing, like changing this. What I would suggest, you just copy and paste it over here somewhere again. Sorry, this one. I have to copy this whole model and paste it again, and then change the gain to, right now I think it was 10. So first one was 10, so assuming this is like 20, I just take 20 to teach you. Then you will run this whole model, then you will see the effect here. This is the same plot, and then what is the next scope? So this, you can see the rise time is changed to 89, which is quite high as you increase the gain value. So this effect you want to learn from here, and then you can in order to find out the steady state error, you will double click on this scope. You will see the steady state error is nothing, just showing you that the end behavior of the graph. Initially this one is starting from 0 going to the step value of 0.8. so in the meantime, so you would reduce, you will subtract the actual value from the reference value, and this will give you. So over here, if you take a look here, this is 0.2. steady state error is 0.2%. so you can just grab this figure, copy this figure into your notebook, and just copy and paste it over there somewhere here. So let me copy over here. So the first figure is the scope for the step response, and the second figure is the scope for the steady state error. You will do the same process for the first order transfer function and the second order transfer function, and follow these guidelines. Like this page number 14, you will complete figure 12, you will complete figure 13, and so on. All these figures, they're nothing. So the rise time, as I mentioned, you can find out from there, and steady state error from there, and you will do the same for the second order response. What is the effect of adding the p value, the kp gain value, and then you will also use the PID controller. Let me show you the PID controller later on. This is still kp. So let's do one thing for the steady state is 1 over s squared plus 2s. So let me change this one to, what is this, 1 to 12. So let's do this 1 to 12 and hit OK, and see, you can increase this block to see the transfer function. So then you will click on this scope to see. This is a very nice like step response, and you want to take a look of the error. So error initially is always be very high because it is still at 0, it is about 1. So this tells us the rise time. Overshoot is about 40%, and so on. A steady state error is about, this is over here, this is about 0.9 something. You will see the end behavior, find out the steady state error. Then you will do the, what we call the next, this you have learned. By this way you will learn the P controller, and then comes the next controller, which is PD controller. You will keep the same first order plant, and the one which I showed you here, this is the first order plant. G of s is 1 over 0.1s plus 1, and then you will use the PD controller. And where will you find the PD controller? Let's do this. So over here, I'm going to remove this part. I'm going to go to the library and find the controller The continuous, I think I have a controller, PID controller. Look at the continuous. Yes, here we go, the PID controller. You will click on this and drag it into the editor window, and then this is a PID controller. You will just connect this part with this. Let me delete this part here. This I don't want to delete. So that's good. Not sure. Okay, this is good. This looks good to me now. What you have to do in order to get the PD controller, P proportional gain is 10 and derivative gain is 10. So let's double click on this, and you can change the properties here. This is PID, so you go to PD, and then proportional gain is 10 and the derivative gain is 10, and then hit OK. So then you would rerun this program to see the adding PD. You see how nice this is. Before that it was not like this, but now you see the transient response is much better. Rise time has also been stabilized, and so you will keep on doing the PD controller, and with a first order. So you will use this figure 30, figure 31, 32, follow these directions. So let's use the PI controller. The gain is let's do this one. For the gain is 10 and integral gain is 20. So you will double click on this and change from here to PI. The gain is 10 and let's keep this 20, and then hit OK. And then you would see the effect of adding the PI controller before the transfer function. Double click on this and you will see this is the new time response. So it's a little bit rise time is the new rise time is 412 milliseconds. Overshoot is quite reduced now. So this is how you will finish this, the effect of learning the PD controller, PI controller. Now I have to show you the PID controller. So let's use this PID controller for like 30, 20 and 10. So I'm going to change this to PID controller and put this 10, 20 and what was that, 30, 20 and 10. 30, 20 and 10. Let's hit OK and then run it. You see this is a changed plot when we add the PID controller. That's how you will use this PID controller to see the effect of changing the PID controller. And then finally the final figure is the tuning parameter, which is not difficult. What you have to do here, double click on this and you just click on this tune. So hit when you go to the tune. So what do you want to tune? With the rise time, with a, so let's do this. It will take little time to, because this will appear like this. Controller parameters are PID and the rise time, settling time, overshoots, everything is written here. So we want to do this. So once you get this window, PID tuner, so then I would say click on this show parameter. So now right now it is showing us the best transient response is at P, which is 51, I 77, D and 7.5. so then you can change this response time. If it is faster response, you bring it over here and then update it. It will update the P value, I value, the derivative gain value, And then if the system is more robust, means less oscillations, then, or if it is very high oscillations in the transient response, you can see a lot of oscillations here. And what are the new PID gain values? And if you want to make the system slower, you bring this cursor here, the system becomes slower. So this is up to you. What kind of response do you want? And for that response, what is the P value, the KP value, KI value, KD value? And these are the overshoot rise time. And then you can clip it, put it in your notebook here. Thank you guys.